Hello, everyone. So now we are in topic 2 of our syllabus. The topic is on refrigeration and liquefaction. Before we begin, let's uh, describe the objectives for this topic. The first objective is to compute the coefficient of performance for a Carnot refrigeration cycle and recognize that this represents an upper limit for any real refrigeration process. Next, we describe a practical absorption refrigeration process and explain why its use might be advantageous. And next is sketch a cascade refrigeration system, explain when why one might use such a system and understand how to approach the selection of refrigerants for such a system. So refrigeration it implies the maintenance of a temperature below that of the surroundings. I'm pretty sure that you're familiar of refrigerators and air cons. So the uses would be, like I mentioned, air conditioning, preservation of food, transportation of food, manufacture of ice, dehydration of gases, lubricating of oil, and we also need it if we have to conduct low temperature reactions in industries, and also for the separation of volatile hydrocarbons. Since the low temperature must be maintained, therefore, there is a necessity to absorb the heat continually at a low level. And it uses a liquid with low boiling point, so these are the refrigerants, to absorb the heat at low temperature. And just like in a steam cycle or a Rankine cycle, the liquid must return to its original state so it can absorb heat again. Therefore, the series of steps through which the fluid passes constitutes what we call the refrigeration cycle. And here are the types of refrigeration cycle. We have the Carnot refrigeration, vapor refrigeration, and under that we have the standard vapor compression cycle, ordinary vapor compression cycle, and we also have the air refrigeration cycle, and as you can imagine, our fluid here is air. Let's begin with the Carnot refrigeration cycle. Just like in our in our production of our heat topic, the the Carnot cycle is the most efficient cycle. The counterpart in the current topic is the Carnot refrigeration cycle, and it operates in between two constant temperature, the high and low temperature reservoirs, and just like previously, all the processes are reversible. It's actually the reverse of a Carnot engine cycle. So remember in our previous lecture, the cycle in the TS diagram, the cycle goes through a clockwise direction. But later you will notice that we are now moving in a counterclockwise direction on the TS diagram. Um, so let's compare first or differentiate a heat engine between a heat pump. So heat engine, this is what we discussed before. It absorbs heat from a high temperature reservoir to do a net amount of work and then pumps the waste heat into a low temperature reservoir. But for a heat pump, which is the current topic, um, work net is used to absorb heat from a low temperature reservoir and then dump the excess heat to a high temperature reservoir. What's the difference? So obviously, we can see the difference from this slide, but let's discuss it. They are essentially the same devices, but they have different objectives. In the refrigerator, the maintained refrigerated space at a low temperature is maintained at a low temperature by removing heat and discarding the heat to a higher temperature reservoir. In a heat pump, okay. So let me correct. What we're differentiating right now is a refrigerator and a heat pump. Okay, not a heat engine and a heat pump. Okay, so between a refrigerator and a heat pump, um, so heat pump maintained heated space at a high temperature. This is accomplished by absorbing heat from a low temperature. Example, heater during winter. So again, the difference between refrigerator and a heat pump. So you know already what a refrigerator is. We have to maintain a low temperature inside the refrigerator. That's the objective of the refrigerator. But maybe since it's very hot in the Philippines, uh, we don't usually use heat pumps. But for heat pumps, the goal is to maintain a heated space. So imagine you're in a winter season and we want to maintain the hot temperature inside the room. So that's the heat pump. I hope it's clear. Next, we discuss the Carnot refrigeration cycle. It consists of two isothermal steps: heat absorption at low temperature and heat rejection at high temperature. So just like our Carnot engine cycle, but in the opposite direction. And also two adiabatic and reversible steps, the compression and expansion steps. So let's discuss what is the coefficient of performance. So in our previous lecture, production of power of heat, our measure for performance is the efficiency, but now we call it the coefficient of performance. So it measures the effectiveness of the refrigerator. It's defined It's defined as the heat absorbed at the low temperature because in a refrigerator, that's your goal. Absorb the heat at a low temperature and divided by the work input so, into the compressor. So that is QC over WS, and WS is just actually the difference of QH and QC. Expressing it in terms of temperature would give us the following equation. So just like our Carnot efficiency that we can express in terms of temperature, our COP can also be expressed in terms of temperature, and it gives us the maximum possible of performance for any refrigerator operating between the temperatures TH and TC. Just like uh, the COP of before, okay, just like in the previous lecture, the COP of a Carnot cycle is independent of the refrigerant, but dependent on the two operating temperatures, TH and TC. So there's no way that we factor in the type of refrigerant in this equation. We simply need to know the low and high temperatures. Okay, next is the diagram for a Carnot refrigeration cycle. So again, we have four devices, the compressor, condenser, the turbine or expander, but we usually in actual refrigerators, this device is replaced by valves or expanders and the evaporator. So work is done on the compressor, adiabatically and isentropically. Now, our refrigerant from wet vapor becomes saturated vapor upon passing the compressor. So, next it moves to the condenser where it uh, discharges the heat into the high temperature reservoir, and it does this at constant temperature so that our saturated vapor becomes saturated liquid. But still, remember, since we're dealing with saturated liquid, it happens at a constant temperature. Now, it passes through the turbine or expander adiabatically and isentropically, uh, producing a small amount of work, okay, an amount of work, and it transforms the saturated liquid to wet vapor. And finally, in the evaporator, this is where uh, heat from a low temperature reservoir is absorbed at a constant temperature, and the wet vapor remains as a wet vapor. So maybe you're curious, uh, well, in the old refrigerators, not sure if you still have an old refrigerator at home. At the back of the refrigerator, there's like a parang grills at the back of the refrigerator. Before, if we want to dry our clothes, we just put at the back of the refrigerator. It's actually the condenser. So I was very delighted to know uh, years after that our sampayan was actually the condenser of the refrigerator. Okay, so we have the evaporator, this uh, where the heat is absorbed at the low temperature, and then D is a capillary, other parts. So I can't find the expander or the turbine here, but anyway, so we have the compressor, the condenser, evaporator. And this is what an air condition looks like inside. Not sure if you have tinkered with your aircon before. We also have the compressor, evaporate. So the one that's in front, in a window type aircon, the one that's in front are actually the evaporator coils. And we also have the condenser, uh, I mean the compressor, and here is the condenser. So where is the, anyway, they do not include the expander. Anyway, let's proceed. So this is how the Carnot cycle looks like on a TS diagram. Just it just looks like the Carnot engine cycle, right? But what do you notice? We're moving in the counterclockwise direction. So this is the compressor. This is the uh, condenser. Okay, compressor, condenser, expander, and then evaporator. So compressor, we move just like before, diba? The movement is from bottom to top, and the expansion is from top to bottom. Compression, and then condense, and then expansion, evaporation. Right. QL or QC is absorbed here, it's dumped here at the top in the condenser. Let's skip first the sample. Let's just answer the examples in the next lecture. So, what are the impracticalities of a Carnot refrigeration cycle? First, process 2 to 3 and 4 to 1 cannot happen in real life because they are uh, reversible and isentropic. So the movement is actually should be towards a higher entropy, so slanted to the right. Process 2 to 3 will require a compressor that will handle two phases. So that would be a problem because we're inside the saturated region. Process 4 to 1 involves expansion of a high moisture refrigerant inside a turbine. So just like the problem before, if the moisture is high, then that will cause problems. Therefore, execute outside the saturated region. I execute outside the and instead of a turbine, use an expansion engine to avoid the erosion problems of the turbine. So this is the vapor compression cycle. Uh, so we to solve the impracticalities of the Carnot cycle refrigeration cycle, we propose they propose the vapor compression cycle. So it's liquid evaporating at a constant pressure instead of constant temperature in the Carnot cycle. And it provides a means for heat absorption at constant temperature inside the saturated curve. But since we want to move away or outside the saturated curve, we still the process still happens at a constant pressure. Likewise, condensation of the vapor. Ah, okay, sorry. So this is the evaporation part. Okay, evaporation part at the bottom of the TS diagram. So what I'm talking about earlier is actually the condensation of vapor that moves away from the saturated curve. So condensation of a vapor after compression at higher P provides the heat rejection at temperature, constant temperature. The liquid from the condenser is returned to its original state by expansion process. So replace it, replace the turbine by an expander. Use refrigerant with low boiling point. So we have two types, the standard vapor compression cycle and the ordinary vapor compression cycle. For the standard vapor compression cycle, it consists of two isentropic processes and two isobaric process. So remember, before in the Carnot cycle, this is a two isothermal process. But for the standard vapor, uh, we're now dealing with two isobaric process. Yun, and we now use expansion engine. Okay. So this is the process diagram. Okay, so compressor transform our saturated vapor. Now, instead of just saturated vapor here to superheated vapor. Okay. And condensing at constant pressure releases the heat and transform the liquid to saturated liquid. Now, instead of turbine, we replace it by an expander. So, by the way, the assumption for a standard vapor cycle is still for the compression and expansion process happens adiabatically and isentropically. Okay. And then for the last step, the wet vapor is transformed to a saturated vapor at constant pressure. So you have to note the differences between the standard vapor cycle, standard vapor refrigeration cycle, um, yeah, with the Carnot cycle. So, yeah, and this is how it looks like on a TS diagram. Our compression now begins with a saturated vapor and ends with a superheated vapor. Okay, and then this happens at constant pressure. The condensing part releasing QH. And as for the expansion, we're inside the saturated curve, but that's all right. We're using an expansion and engine. Okay, so this happens at constant pressure. This happens at constant pressure. All right. So that solved the impracticalities of a Carnot cycle. So what about its COP? So we perform an energy balance, but this work uh, workout is significantly smaller compared to the work input. So we assume that this value is negligible. And using the definition of a COP, coefficient of performance, we then uh, substitute, okay, the enthalpies, okay, for each step. So you use the okay, you please use the assignment of the points. So QH is HC minus HB and QC is HA minus HD. So replace that in the equation. Oh, just a minute. HB minus HC. Okay. So anyway, it's because naka absolute sign and then just replace it in the equation. You will get the equation for the COP. If we want to know the mass of flowing stream or the mass flow rate of the refrigerant, we just divide QC if it is uh, in terms of unit time with the difference in the enthalpy to get the mass flow rate. Okay? What about the other type of vapor compression cycle, the ordinary type? Okay. So instead of two isentropic processes, one is replaced, the expansion part is replaced by an isenthalpic process. Okay? So kanina dalawang isentropic process to, but now the expansion is isentropic because we replace the expansion engine with a throttle valve. So remember in the throttle valve it's isentropic. Compared to the previous standard vapor compression cycle, this is less expensive. Okay, so mainly the difference compared before is this one, the throttle valve. And because it's a throttle valve, H is constant. Okay. Um, so this is the same as the one I showed before for ordinary compression vapor compression cycle. So you use a throttle valve. And for the COP, okay, um, using the same equation as a standard vapor compression, but since HC is equal to HD, okay, HC is equal to HD, right? This is isenthalpic. Our COP becomes simplified to this equation. And we also use the same equation for the mass of flowing stream or the mass flow rate of the refrigerant. We now move on to the types of refrigerants. What are the characteristics of a good refrigerant? It should not be toxic, not flammable. Uh, the cost should be acceptable, should not corrode our device or our refrigerator or aircon. And this is important as well, the vapor pressure in relation to temperature. So the vapor pressure inside the evaporator must be greater than um, the pressure of the evaporator should be greater than atmospheric pressure to avoid leakage. So some examples of refrigerants. We have ammonia. This one is called chloromethane, carbon dioxide, and this one is propane and other hydrocarbons. We also have halogenated chlorofluorocarbons, like trichlorofluoromethane, CFC12, dichlorofluoromethane, CFC11, and CFC12. Hydrochlorofluorocarbons can cause relatively little ozone depletion. Um, Hydrofluorocarbons, which has no chlorine, can cause no ozone depletion. For example, tetrafluoroethene, the properties of which you can see in table in Van Ness, and the thermodynamic properties, so like the steam table for this refrigerant. And then the pH diagram is also found in Van Ness. We also have pentafluoroethane. So this is the properties of thermodynamic properties of tetrafluoroethane. So like we're given the temperature, pressure, and the specific volume, enthalpy, and entropy. And, and then we're also given the pH diagram of tetrafluoroethane. So by the way, I actually posted at uh, an expanded version of this table in the Google Classroom. The thermodynamic properties of tetrafluoroethane. You can see it in the Google Classroom or the refrigerant R134A. And also this one, I posted it in the Google Classroom, the thermodynamic diagrams, figure G point, let me check, figure F.2 for uh, the 8th edition of Van Ness. So F.2. So please check the Google Classroom and we will use it in solving some of the problems for this topic. Now we've discussed the energy efficiency ratio. So instead of COP, it's a more recent measure to evaluate the efficiency of an aircon. It's the ratio of the cooling capacity to the total power input. Okay, so higher EER means more efficient motor with less consumption. Next is the energy efficient factor. It's also a measure of efficiency of the refrigerator, and it's actually the ratio of the volume in liters to the energy consumption. So high EF means more efficient motor. Not sure if um when you go to appliance stores and you can see like this label, yellow label. For refrigerator, it's called the energy efficiency factor. For the aircon, energy efficiency ratio. And so the higher this number, the more efficient the motor with less electricity consumption. So now you know when you're shopping for aircon and refrigerators. Let's answer this problem in the next lecture and proceed with air refrigeration cycle. Um, it uses air. So another type of refrigeration cycle using air as refrigerant. The disadvantage is that there's no change in phase yet with suitable compression expansion technology, air can be practical. So the disadvantage, there's no change in phase, but because of the high tech mm, technology nowadays, using air is like because it's abundant, right? So it's practical and it does not damage the environment. It consists of two isentropic. The cycle consists of two isentropic and two isobaric processes. It can deliver temperatures down to negative 100 degrees Celsius or in the range of negative 50 to negative 100. It's cost effective for cryogenics and food freezing, um, and also so it's commonly used in food sector, and also like in the refrigerated transport, like refrigerated trucks and cargos. And it's also used for integrated rapid heating and cooling, or what we call cook, chill, freeze. Also used in the food industry. And this is the process diagram of the air refrigeration cycle. Uh, so just like in the standard vapor compression cycle, we use a compressor and expander adiabatically and isentropically. And then, instead of a condenser, this one is a cooler. Heat release and heat absorb happens at constant pressure. So these are isobaric steps. For the energy balance, uh, simply we can equate Q, the difference between the heat is our net work. And then we can use, if we assume ideal gas, we can use the definition of, we can use MCP delta T to calculate QH and QC. Next, we have the cascade refrigeration cycle. Does this look familiar? It's just like our binary cycle in the previous lecture. So the cascade refrigeration cycle are two or more refrigeration cycles operated in series. And we do that because we want to achieve very low temperatures. thus increasing the COP of the refrigeration. So what happens here? We have the high temperature reservoir, low temperature reservoir. This is the first cycle. The condenser of the first cycle is actually the evaporator of the second cycle. So there's a heat exchanger right here. Okay. So we now proceed to the liquefaction process. Liquefaction happens when a gas is cooled to a temperature in two in the two-phase region. What are the applications of the liquefaction process? Scientific, industrial, and commercial. Um, Gases can be liquefied by the following: heat exchange at constant pressure, expansion of a gas in a work-producing device, or a throttling process. So, where do we use liquefied gases? Example, in propane in cylinders as fuel, or natural gas for ocean transport. Liquid nitrogen provides low temperature refrigeration. And for example, liquefied air, gas mixture are liquefied for into their component species by distillation. Not sure if you're using liquefied LPG, liquefied petroleum gas at home. So that's one of the uses of liquefaction. And again, um, what's the convenience of a liquefied gas? It's easier to transport liquefied gases compared to their uh, normal, natural form. Okay. Because liquids have It's easier to transport because liquids have lower specific volume compared to their gas counterpart. We have two types of liquefaction process. The lean liquefaction process and the cloud liquefaction process. Okay. Lind and cloud liquefaction process. I checked the pronunciation. Um, First, the Lind liquefaction process. So we begin at the compressor where work is done on the compressor. We also input the gas here. Pre-cooling is done. Afterwards, the gas goes to the cooler, and then the throttle valve. Now, in the separator, the liquid is separated from the gas, and this is our product, the liquefied gas. Z is the fraction of the gas that is liquefied. Therefore, if this is Z, then this should be 1 minus Z, right? And the process repeats in a cycle. How does it look like on the TS diagram? If this is our process diagram, okay, what's the difference here? Okay, the difference is for this one, there's no pre-cooler. So the heat exchanger is actually the cooler here. Um, and as you will notice, our process actually exits the saturation curve. Okay, and this part right here is important. This is the separator. Part of the gas would be liquefied, okay, right here. And then part of it will remain as vapor. So this is point 4. Okay. Let's assume a steady state process and do an energy balance around the coolers, throttle valve, and separator. Assuming an adiabatic process and there's no shaft work, this is our energy balance. Uh, Considering the mass fractions, therefore, uh, our delta H, we can express the delta H in terms of the enthalpies. Okay, so again, this is our energy balance. We assume Q equal to 0. There's no shaft work. So therefore, delta H is 0. And then expressing them in terms of enthalpies and considering the mass fraction, this is our energy balance. So by the way, this numbering right here is based on the figure right here. Okay, so use this figure right here for this equation. Okay, let's skip the example first and move to the Claude liquefaction process. So the difference is that instead of a throttle valve, an expansion engine is used. But essentially, they are the same, except for this part. Again, this is for Claude. For Lind, we use a throttle valve. And we can also do an energy balance around these three devices to solve for the mass fraction. Okay, that ends the lecture part of our topic on refrigeration and liquefaction. The next lecture will deal with the problem solving. Thank you.